Okay, so I'm going to start talking about Prolog, and Prolog is a supplemental lecture that is available from the bhacker.com website, and it is available in the AI class. If you go into the AI, Artificial Intelligence class, and you look at the tutorials, right here, you'll see tutorials on Prolog, Lisp, and Scheme. These are different. Actually, the Lisp and the Scheme are the different ones that I've gone over in class so far. The Prolog one is the one I'm going over today. It is not part, not so you're not confusing, it's not part of this series that's called Prolog Lectures. This is totally different. I'm going to cover these guys next time we meet. So this weekend ends with Prolog, and then we talk about Prolog and Artificial Intelligence on Friday, the next time we meet together. So just to clarify where you can find this, because you might want to look for this lecture when you're starting to do one of the assignments, which is the last assignment. Assignment number 4 is going to have you work with Prolog. So what is this Prolog? What am I talking about? Well, we're going to probably be using what's called Strawberry Prolog for this course. And let's run through the install, actually. That's not a bad idea, so we can see what we're looking at first, and then I'll run through the fundamentals of the language. So I've got a Windows parallel disk here, and I'm going to open up my web browser, and I'm going to type in Strawberry Prolog. And I'm going to see what happens. So I've got Google here. I'm going to type in strawberry, like the fruit, Strawberry Prolog. Prolog. And I'm going to see Strawberry Prolog coming up. And I'm going to click on it. It's the first one that comes up, actually. So if you don't want to type in Strawberry Prolog and you just want the URL, it's www.dobrev.com. But strawberry is a little bit easier to remember, I think. And you'll see that there's a little picture of a strawberry on here, too. So click on the download link. And there's a couple of different versions of it. It is free. There's a couple of different versions of Prolog. You don't have to use Strawberry. Strawberry's nice because it has like a little interface to it. It has a little GUI, just kind of like Scheme. But there's different versions of Prolog. Click on the Lite edition here, and it'll start to take you to a download screen. And let's see, this is for Vista XP. There's also a version, I believe, that will work on Windows 7. It might actually be the XP version. It might be the Prolog 3.0 beta. You can use the 2.9, you can use the 3.0, you can use any version you want. I'm going to use the 2.9 too because I'm working on an XP system. There's a beta of another version of probably works. In fact, the XP system works with Windows 7 as well, depending upon what you have. So I'm going to save the file to my local disk, and you see it's actually smaller than Scheme. And it should hopefully install for me, and I'm going to install it in a few minutes here. So now I have this little thing that says Prolog on an icon, a little box, a little object here. I'm going to double click on it, run through the install, and you'll see it's going to be very similar to the Scheme version. So this program is property of Dimitar Dobrov or whatever. That's his name. So it says it's working on Vista and XP. I can't pronounce his name. Alright, so I'm going to go unzip, and 310 files were unzipped correctly, and the install should start for me automatically, which it does. Do you want a shortcut to Prolog Games to the start menu? Oh, no, I'm not going to do that. I'll just leave it on here. So it's going to say it installed it successfully to the folder. Very good. And then I have this little icon, it looks like a strawberry, that appeared on my desktop. I probably did this a little bit faster. Some of you are probably still downloading it, so I'll kind of go through this a little bit slowly, and I'll show you kind of like what it looks like. So I double-clicked on the little icon that was on my desktop. If not, you can go to the Start menu. You can see it here, Strawberry Prolog, little strawberry. So very similar to Scheme, except for it's a completely different language. And what we have here in Strawberry Prolog is over here we have the factorial.pro, which is the file that we're putting the Prolog program in. And then over here we have the output screen. So you can write over here, and you can run over here, or you can load a file in over here. So if I press run, and I go run, it's going to run this thing for me. And then what rang for me was this really nice little GUI thing that comes up with a bunch of stuff that's randomly put on there. Prolog does a little bit more than that, however. It does all sorts of things, and then I'm going to run through the lecture and show you what it does. But it's very similar to Scheme, so I don't really have to show you too much of the interaction, except for that we have a couple different syntax notations that's a little bit different. We put a period at the end of each line, so when you type something in, you put a period at the end. There's interactive modes where it's going to show you the output if it's a what do you call it, a command line thing versus a GUI thing. That loaded up a GUI screen. But that's how you're going to be able to tell if your Prolog is installed correctly, is when you get that little, if you run the program and you get this little screen that comes up here, it says factals, find the target, then you know everything's installed correctly and everything's running correctly. So you can also close the window, open up other windows, or also close the output window. You can go like File, New, and open up a new Strawberry project. And if you're opening up a new Strawberry project or a new Strawberry file, it'll open it up here. And then you're able to type stuff in, like house, friend, or something. I don't know, just type basically some stuff in and put a period next to it. It should come back and say nothing. Then it comes back and highlights it as green. There's a color coding kind of system to it where I can say, put a fact in, and I actually have to show you what Prolog's all about before you can actually see it work. But what you're going to get is a sort of an interactive mode that's sort of running in an output-input mode as well. So it's a little bit different, but let me talk about what this is so we can actually kind of see it work. Another thing you might be interested in knowing is that there's a lot of help available for Prolog. In fact, if you go into the help menu, it used to take you out to a website where you can link into it and say, it's like, let's say how to, let's say, hold on a second, go into the language and go built-in predicates. Well, we don't know what predicates are yet, but you'll see some loop examples, type checking, windows, a bunch of other stuff that's in here, warnings, example programs. So if you click on example programs, here's a simple Lisp interpreter. So I'm going to click on that. We go, oh, this is Lisp.pro. So in your samples directory, you're going to see, in fact, if you go out to the hard drive, you'll see from the Windows Explorer, let's see, let me go to Explorer actually. I clicked on the wrong button here. You'll see a help directory, or you used to be able to see a help directory. Let me just make sure I can still see it. Let's see, it's going to be in program files and Strawberry Prolog. And then we have games out here, so there's a bunch of games and stuff that come with it. Examples here, and the examples we're going to see SPJ for Strawberry Prolog. There used to be a help. Well, here's programs. Let's see. My programs, functions. So what is so now I have to basically tell you what Prolog is doing, so you can figure out what you're supposed to type in the window. So let's take a look. And so that's the order of business next. So I'm going to leave this window up and go back to the PowerPoint. And then we can sort of see how these pieces come together and what it is we're supposed to be doing with Prolog. So what is Prolog? Prolog is a programming logic program. So artificial intelligence uses Prolog not like Lisp. Lisp and Scheme are used to process data. We've done a bunch of experiments. We have thousands of data sets. We want to take this list and cross it with that list and see what the difference is. Or we want to figure out what we found. Prolog is used in a slightly different fashion. It can be used for lists. We can still do the same things. In fact, there's list support. So Lisp, L-I-S-P, Lisp support for lists is included with Prolog. And then Prolog also has capabilities for keeping databases of information and for programming logic. So it's the most widely used logic programming language, and it's probably one of the first ones that came around. It was developed in the 1970s. It's good for knowledge representation, natural language processing, state space searching like the Rubik's Cube, and there's an example of the Rubik's Cube in this lecture, expert systems, deductive databases, and agents. So hopefully some of those words are making sound familiar to you after a weekend of listening to me talk about all these different concepts. They're used to program these concepts. So you can make an agent with it, you can make a family tree and solve problems in terms of who's related to who, and draw correlations and basically perform logic with data. So the main idea is you ask the computer to solve a problem using principal logic. You put in a bunch of facts, you put in a bunch of rules, and then you say, hey, is it going to rain? And it comes back and says yes, or no, and we'll go through a couple of those scenarios in a few minutes as well. So the program states the known facts. So you ask it a question, you make a statement about the computer, or about the search, or about the proof, and then and Prolog will come back and say true or false. See, Scheme doesn't come back and say true or false. Scheme comes back and says 9. You know, if you put factorial something in there, and it comes back with an answer for you, and it solves and gives you an answer. Prolog is yes, no, or true or false, depending upon the version of Prolog that you're working with. So it's going to do its own analysis, and it's going to do its own thinking. So it's not running a function, but you can write functions in Prolog. Instead, it's giving you logical evaluations of expressions. So additional mechanisms are provided to guide and search to find a proof for something. So again, going back to the declarative versus the imperative language constructs, this is a declarative language because we're declaring that X is equal to something, and we're declaring that Joe likes pizza, and we're declaring, you know, that Joe also is tall, and then Mary's tall, and then we can ask Prolog, well, does Mary like pizza? And if the rule says all tall people like pizza and Mary's tall, then of course she likes pizza. So then it comes back and says, hey, yeah, Mary likes pizza, which is what we're using Prolog for. Because what ends up happening is you run through, and this was done by a lot of psychiatrists who were keeping track of patient information, to say that, you know, all these people who had this particular problem also experienced this problem over here. And all these people, and then you find the correlations between all of the data. Then you can ask Prolog, what does Bob have? It comes back, or it can say, does Bob have this? It comes back and says, yeah, Bob's got this, or no, Bob doesn't have this. So it saves the psychiatrist, or saves the developer or the AI person time, because you have the automation built in with the logic of the programming system. All right, so it's called a declarative language because the programs are written in consistent declarations versus programming language statements, and which is a lot different from other procedural or functional languages. So programming and logic language is not procedural. We don't put in, there's no main program, just like Scheme. There's no main, there's no iteration or flow control. So programs in these languages state how a result is going to be computed. So instead, we supply the computer with a couple of components, facts and rules. So we have the relevant information, the facts and the rules, and then the method for the inference for computing the desired result from the facts and the rules. So the logical programming is also based upon what's called predicate calculus, which is the form of math where it comes from in terms of the logic. So here's our first logic background. It all started out with this concept of the Horn clauses. So if A1 and A2 and A3, then H. And then we have the head being H, and then we have the body as being A1, A2, A3, whatever happens to be enclosed. So an example is, if X is positive and Y is negative, then Y is less than X. So we put a bunch of statements in there like that, and we say, you know, this is the case. And we're basically stating the facts, and then we'll state the rules that are associated with it, and then we ask Prolog questions. So when you build and you put the program in one screen in the program area, you're building the program logic, whether it be a database or whether it be a series of questions. And what you're going to be doing is building a database for one of the assignments. And the database for one of the assignments is going to be a family tree. And you're going to be able to ask the family tree, who's Bob related to? Everybody's family got a Bob in it, right? No, I don't know. And you figure out who Bob is related. Is Bob related to Mary? Comes back and says, no. Bob's not married. Bob's not in your database. Oh, okay. So it'll come back with a yes or no, though. So in terms of the predicate calculus, we've got the proposition. So the main base is the proposition. Proposition is a logical statement made up of objects and their relationships to each other. So it may or may not be true. As an example here, we have man, John, and then we have likes pizza, basketball, or baseball. So it looks like a functor, or it is a functor. It looks like a function. Not really a function, it's a functor, where we've got man, and we're defining man as John. So this in C++ or C, Java would be equivalent of saying, string man is equal to John. But it's not really that way. We're not using it like a variable. Instead, we're using it as a definition, or proposition, essentially. So then we have different ways of expressing the predicate calculus in terms of the logical connectors. And so these are the common ones you're probably familiar with in other languages. So a compound proposition consists of two or more of these propositions connected by a logical operator. For example, we have the negative, not A, the conjunction A and B, A or B, A is equivalent to B, B implies A implies B, and all the different combinations you possibly can come up with. Because what we're trying to do, can we keep the talking down? It's in the back. Hello? Thank you. I don't want to talk over you and you're way back there. All right, so if we can keep the relationships clear between the components, then we can figure out what the answers to some of these questions are in terms of the explanations. So here we have the qualifiers. The qualifiers are going to tell us everybody in this set, only half of this set, part of this. So this is where your discrete mathematics comes in handy, because then you're going to know the union, the intercept, all of the different ways of expressing the logical operators and the set theory, because it's based on set theory. If you say, here are all the people that passed this test, and here are all the people that passed that test, and here are all the people that failed this test, is Bob going to pass the course and come back and look at this stuff? And the rules will be, well, if passing people for the course means that you've passed this test, and this test, and that was optional, and it comes back and says, yeah, Bob's going to pass. Comes back and, after it looks at the data, given the rules. So the predicate calculus in terms of the quantifiers, the variables may appear in terms of its formulas, but only when introduced by quantifiers. So the universal set for all, or there's existence relationships where it says there exists. So there exists a person, Mary, whose first name is Mary or something. So we have all women are human. There is some sport that Bill likes, meaning that there's some sport. Nobody ever uses this symbolic notation. Instead, we write it out in English words. So just like we don't have to use lambda calculus in a scheme, we can write out, A, E, factorial, all that stuff. Same thing is true for Prolog. You don't have to use any of the cryptic language. You can actually just write it in English. So we have resolution and unification to consider. The resolution is how do logical deductions from multiple horn clauses get evaluated. So if the head of the horn clause, number one, matches one of the terms in the horn clause, or number two, when we can replace the term with the body of the horn clause. So it's like substitution. We can say, well, Bob is tall, and Bob likes pizza, and all tall people like pizza. So Mary's tall, so we can substitute the pizza in there with the tall. So we can take, well, tall people like pizza, and we say, well, does Mary like pizza? Well, then we have that connection between tall people and pizza, and that Mary is tall, so we can make the logical connection, which is what Prolog's doing. That's what Prolog's doing for you. It's doing the connections between the different pieces of data. It's kind of like human thinking, if you think about it. Going back to what I was saying the other day, how do we logically deduce that something is hot? Well, we felt something hot, and we have a memory of burning ourselves because now we know that something is hot. We know what hot means. Until you know what hot means, you don't know. You're going to have to burn yourself eventually to know what the hot means. So, and we know that, and then we sense something else that appears to be hot. We don't have to touch it. We can just think to ourselves, Prolog can come back and tell us, actually, if we can't remember, that that's hot. Don't touch it. Because if you touch something that's hot, you're going to burn yourself. And we have that association between the logic. This was actually, believe it or not, the predecessor research for neural networks. So neural networks are building off of predicate logic in some case, and logic program and logic systems. So there's a ton of different applications for this in terms of being able to predict, being able to analyze, and then deduce information on the fly. But garbage in, garbage out. If you never touched anything hot, as a human, you don't know that it's hot or cold. So that's why people try foods. They don't know if they like something. So how do you know you don't like something if you've never tried it? You know, the age-old question. And then people try and go, well, I don't like it. Well, that's bad logic because you didn't give it a chance. So it's better if you don't try it under that situation. You just try it and you go, oh, I like it. And then you smell it and go, oh, I like that. And then you get that association going on. Anyway, so humans can screw up their own logic by using irrational thinking and not logical thinking to make their own connections. Just like people who don't like anything just because they don't like something. Well, that's because bad logic. So you can call those people irrational. So, all right, so unification, how to determine when a hypothesis are satisfied. As an example, is it going to rain? Well, 10% humidity or precipitation or whatever happens, you know, such and such percentage of cloud cover. You could put weights on this stuff. You could put focus or emphasis or connections on these things. And if you put weights on it, then you're building a neural network because that's going to give weights for priorities, for certain directions of flowing of logic. Because just like we deduce that something is true or false, we come to it from a logical conclusion by making the connections between the data. And just like that, we can perform what's called a map, or we can do a tree, or we can build some sort of a computer science data structure, put the data in there, search the tree, which is what Prolog is doing, and then come up with a conclusion. Or do it backwards and have the tree tell us something, and then we have data mining, if you want to think of it that way. So let's see, resolution. Resolution is an inference rule that allows inferred propositions to be computed from given propositions. So suppose that we have two propositions. We have B that implies A, and then we have D that implies C, and then we can substitute and come up with a new proposition with that. So, and that A is identical to D. Suppose that we rename A to D as T, and then we can say that B implies T, and that C implies, or excuse me, that T also implies D. And then from this form we can infer that B implies C. So we just substitute a rule in, and we can figure out what's going on. So the better the rules, the more substitution can exist, the more logic we can derive out of something. And it mimics human thinking in terms of the concept. So unification is the process of finding values for variables during resolution so that the matching processes can succeed. Instantiation is the temporary binding of the value and a type to a variable to allow unification. So the variable is instantiated only during the resolution process. So we don't really use variables like, you know, x is equal to 1 or anything like that. Instead, we take everything out of the analysis, we assign it to a temporary variable, we use the variable so we don't have to go back through and recalculate. It's like a temporary answer. And then we compare the answer, or we do further analysis on it, on the instantiation, and then we can figure out even more information at that point. So the instantiation lasts only as long as it takes to satisfy one goal, and this is a goal-driven environment. So once you've satisfied the goal, all of the information goes away. So it's not like a scheme where we have to actually come up with a memory footprint because we're going to put some stuff in there, we're going to store the data, and we're going to calculate it. No, this is like come and go. You put the stuff in, use it, don't use it, and then you just load up another database so you can load more information if you want to change your logic. So let's look at the syntax and the terminology, and I'll go through a couple of examples. And you can type this stuff into your Prolog screen if you have it. You can actually put it in a file and run it. Very similar to Scheme. You'll get used to the syntax and you'll get used to the interface as we go through it. I don't actually like this version. I use a different version of Prolog that gives me a terminal window. Just like the GNU Scheme actually gives you a terminal window, and you just type the stuff in the terminal window. And it's just line by line, so there's no loading of a file and unloading of a file. But because you guys are students, you're going to put it in a file probably because you want to save it because you have to turn in your answers somehow. So that's why I recommend Strawberry Prolog. It's a little, and plus you get the little GUI screens and everything. So, but the interface is the same regardless of which version you're using. If you have a MacBook, you may in the past have had Prolog already installed on it. So it's like one of those languages that's open source that's usually available quite easily. So we have the concept of the clause. The clause is equal to the horn clause, which is assumed to be true, which is represented by a head plus some terms. So then we also have and the comma represents the logical and. So this one and that one and that one. So we have commas instead of spaces in Scheme, so the syntax is a lot different. We have a clause that is a fact if no terms are on the right-hand side. So a head and a term are both structures. So our structure is a functor with an argument 1, argument 2. Sort of looks like function notation from Scheme, actually. Represents a logical assertion. So teaches Barbara, comma, class. So that would be that we have that association between, and this is what we would type in. We put a dot at the end, not a semicolon. So each statement is terminated by a dot. If you're going to load up a bunch of data, you don't have to put the dot in. You can just go teaches Barbara, comma, class. Students take, comma, basically you're just stating facts or assertions. So constants are numbers that are represented by strings starting with lowercase. So we have variables that start with uppercase letters. So all of our variables have uppercase letters, all of our constants have lowercase letters. And the goal or the query is the clause with no left-hand side. This is the prompt. We say raining in Seattle, rainy Seattle. It comes back and it'll say true or false. So tell Prolog interpreter to see if it can prove the clause. So it's a it's either a Boolean, it's going to be true or false in terms of the answer. Facts, rules, and queries. So a collection of facts and rules is called the knowledge database. So what you're going to be doing in one of the assignments that's due for November 8th, the last one actually, is to type in a bunch of facts and a bunch of rules, create a database. And the database you're going to create, I believe, is a family tree. And then you're going to ask it questions. And it'll be able to answer like who's associated with who, or is someone associated with somebody else. Prolog programs are called knowledge databases. You fill it up with a bunch of facts and rules. And you can use Prolog programs by posing queries. So we load it up, we run a query. Very similar to Scheme, where you load up Scheme with functions and then you run the functions. So you load up the facts, you load up the rules, and then you run a query on it. You ask it questions, which is the interface. So here's a sample knowledge base where we have woman Janet, woman Stacy plays flute, Stacy. And we can ask Prolog, woman Stacy? Prolog answers yes. So if you loaded this stuff into as facts, open up a blank sheet on the left-hand side, load this stuff up, say run, and then underneath it actually just put in the, woman Stacy with a dot. Make sure you put the dot at the end. So remember, these don't have dots at the end because we're loading up the information. The dot tells us that we're done. So we're done typing this stuff in. And now you can actually type this stuff in if you wanted to, and you can see what it looks like. And it's not going to come back and say, it's not going to say Prolog answers. It's going to come back, either say true or false or yes or no, depending upon the version of Prolog that you're using. So here's using the knowledge base that plays flute Stacy. So the answer is going to be yes. I'm actually, let's go this way. I'm kind of curious because I haven't used this version in quite some time. If and it went to sleep already. Let's get rid of this here. See how successful I can be at this. Hold on one second. Let me just refresh my memory here. Woman Janet, woman Stacy plays flute, Stacy. Woman Janet, woman Stacy. Well, okay, I was going to type it in, but I don't know. My typing is really bad, and I don't want to go back and forth. But what I was basically going to do is type all that stuff in over there and then run it. And you run it on the right-hand side, it should say yes or no, depending upon what it is you're looking at. You guys can play around with it while you're bored. While I'm talking and you're bored. So after we type this stuff in, the thing that you want to keep in consideration is you have to put the dot at the end. And once you put the dot on the end, it'll run it for you. There's also a button that says run. So select the menu item, come back and say yes or no. So then here it says plays flute Stacy. Prolog says yes. Plays flute Mary. Prolog answers, are you kidding me? No, it doesn't answer that way. It just says no, probably. So because Mary doesn't play the flute, there's no Mary in there. There's a Stacy and a Janet, but there's no Mary. So it's going to come back and it's going to say no. There's no Mary in there. So then we have elements of Prolog in terms of the facts, the rules, and the queries. So a fact statement is a proposition that are assumed to be true, such as female Janet, dot. And remember, see, you can see the dot at the end here. Male Steve, dot. Brother Steve, comma, Janet. And then remember that the propositions have no intrinsic semantics to them, and they mean what the programmer intends for them to mean, which is interesting. So you can put all this stuff in here and then have some weird association that doesn't make any logical sense. Because Prolog is not going to judge your logic, and so it's not going to know that, I don't know, somebody can't do something. You know, dog bark, Mary bark, you know, doesn't know if Mary is a dog or a human, so it's not going to be able to figure out logical stuff. It's only what the programmer puts in, so I always go back to that garbage in, garbage out kind of thing. So that's how we put the facts in. The other thing we have to put in are the rules. So after we load it up with a bunch of facts, you can put the rules in first and the facts in second if you want. Doesn't really matter what order. There's no order at all to even any of the facts. So you put the facts in and you have the elements that say that the rules combined with the facts increases the knowledge of the system. And here's one. It says son x, y, and then the rules are associated with the colon and the minus sign. With a space, it says male x, comma, child x, y, with a period at the end of the statement. This is valid Prolog syntax that you can type in. This rule says that x is the son of y if x is male and x is a child of y. So he's a son because he's male and he's a child of y. So x is a son in terms of this definition. And we're calling it son. So not like a function where we say function factorial is equal to something. Instead we have son defined. So now we can have other rules. So these rule statements take in the form of the consequence versus the antecedent. So this is going to lead to this consequence. So if male x and child x or y, then the consequence is that they're a son. And you can do that with parent, grandparent, brother, sister, mother, father, all of the different combinations. So the consequence must be a single term, while the antecedents here, these things that lead up to the consequence may be single terms or they might be a conjunction of multiple terms. Here's an example. Parent x comma y is a mother x comma y. Parent x comma y is also a father x comma y. So we have two that lead up. So we can search for parent and mother separate questions or separate queries. Grandparent x comma y, well, this is going to be equal to parent xy and parent yz. So we can come up with two different combinations from both sides to equal the grandparent. So, and then finally we have the goal. So we have the rules, the facts, and the goals. The goal is the proposition that we want the system to either prove or disprove. Does Mary play the flute? So, or something like that. So when variables are included, the system identifies instantiations of the variables, which makes the propositions to be true or false, or true. If variables are included, and it is true. So as long as Prolog attempts to solve the goal, it examines the facts and the rules in the database from top down. So it starts at the top of the database, works sequentially from the beginning to the end, which means the older data is searched first, and then the newer data is searched to last. So it actually matters which order you put it in, but it's not necessarily significant if the connection is not related. Because you can put data about father and grandparents, and then you can also put weather data in there. And if you cross weather data with family tree data and you ask it a question about the weather, it might make a mistake if it finds something about the family tree that's relevant. Because you had, I don't know, there was a guy named Leaf or something, or there was a guy named precipitation or something, and it matched, and then the rule substituted in incorrectly. So again, it's only as logical as the human makes it. So the elements here, we ask the Prolog the virtual machine question composed at a question prompt. So in some interpreters, we actually will get the question prompt, depending upon which version of Strawberry, or which version of Prolog you're using. And here's how we ask it a question. We say, son Bob, comma, Harry, with a dot at the end, and it comes back and says yes. King Bob, comma, France, no. Comes back and says no, because it doesn't find. If they're not going to find it in there, it's not in the database, they'll come back and say no, not in the database. So we can bind answers to questions to variables. So who is Bob the son of? X is equal to Harry. So if X is equal to Harry, who's Bob the son of? Then we can say son Bob, comma X. And then who is male? X is equal to Bob and Harry. And so we say male X. And then we say if Bob is the son of someone, it'll come back and say yes. If he is actually a son of somebody, so we leave this is a wild card that says Bob, comma, empty. I mean, is Bob in there? Then it says son, and it's going to come back and give us the matching set for who Bob is the son of, or one of the, from the father or the mother, depending upon what it finds, actually. No variables are bound in this particular case. They're used for simple substitution and for each one of the queries that's being run. So we can't have any global variables that come through and say, what's X? It's not like an imperative programming language. So we have the concept of backtracking. So how are the questions resolved? There's forward and backward chaining that exists, and this is a concept of artificial intelligence that's covered in the textbook that is part of why we're looking at Prolog. It does a great job at following these traditional kind of methodologies. So recalling the rule that son XY was equal to male X and child XY, forward chaining is bottom up, starts with each one of the rules and then checks the facts. So when we go back or we go forward, it depends on, we're going to start with the rules, check the facts, start with the facts, check against a rule, and then we can do what's called chaining, which is either I'm going to start with a conclusion and I'm going to prove it true or false, or I'm going to start with an unknown and then derive at a conclusion. So you're proving either a hypothesis is true in the first case or false, which is what Prolog is actually doing because it's working with backward chaining. You know, you're saying, is it going to rain? Or it will rain. And Prolog is going to come back and say, no, it's not going to rain. Or you can start with the exact opposite theory and say, you know, tell me, what do you think about the weather? And it's going to run through and it's going to rain. So it's kind of different ways of thinking. Prolog actually does both. By default, we start with conclusion and we work backwards through the rules back to the facts to say yes or no, in terms of, and that's the basic standard form of Prolog. So it starts with each one of the rules and checks the facts in a forward chaining bottom up. So in forward chaining, we use the database to systematically generate new theorems until one matches the query is found, and then we can run it. So we can say father Bob, man X, father X, given the goal, man Bob. We work forward from the goal to the information that we're looking for, from the bottom of the tree all the way up to the top. Think of it like a tree, if that makes any sense. So under forward chaining, father Bob is matched against father X to derive the new fact, man Bob. So in the database, so the new fact satisfies the goal, and we've concluded and we found our answer. Versus backward chaining, which is from the top down. So we can start at the bottom details or start at the top details. Start with the facts and use the rules that apply to the facts to tell us if the answer is correct or not. So use the goal to work backwards to a fact. So example, given that man is a Bob and as the goal, we're trying to see if Bob's a man, then we're going to match against man X to create a new goal, father Bob, and then the new goal is going to match a pre-existing fact, thus the query would hopefully be satisfied at that point. If we can find a fact that matches it, then we can say yes or no to it. So forward versus backward chaining. The bottom-up resolution is referred to as the forward. Searches the database and the rule facts, the facts and the rules, and attempts to find a sequence of matches within the database to satisfy the goal. Works more efficiently on databases that do not hold a lot of facts and rules. If the database is small, we can search through the facts through the rules. If the database is big, it makes much more sense to do a top-down resolution or backward chaining. So it starts with the goal and then searches through the database to find a sequence of rules and facts that satisfy the goal. If we can find something, then we can say it's gonna be true. So it's think of this the way top-down resolution or backward chaining and the way that Prolog thinks is just how primitive humans think. If you think about a kid and you say that it never rains in California, And the kid will come back and say, yeah, it does. And we go, well, why? No, it doesn't rain in California. Or no, you can't eat this before you do this or something. You'd say something in terms of a rule, and the primitive kind of thinking would come back and say, no, it doesn't. It rains in California. It just rained. In 2009, it rained in California or something, even though it does rain in California. As long as you can find one instance in the database that proves it to be true, then it's true. Which is primitive, because you're looking at maybe a piece of bad information, or you're looking at maybe a rule that doesn't always apply. To say, well, little so-and-so did that, and they didn't get in trouble, then that means I can't get in trouble for this, which is kind of the primitive sort of way of thinking. So there's ways of changing the logic and programming the order in which the rules are evaluated, either forward or backward, to make the answer more relevant, to make the answer more, because essentially what you can do is break the system by coming up with a bad rule or a bad fact. To say, all students who go to ITU have to take this class. But then one student says, hey, actually it was sort of like joint seminar. For a while they said, all students have to take joint seminar. But then a couple students came up and said, well, so-and-so graduated and they didn't take joint seminar. Oh, well, then all students don't have to take the joint seminar anymore. So all of a sudden, and that's backward chaining. It's going back through and looking at the bottom, looking at all the facts of all the results of everything that's happened, and working it back up through the rule system to say, well, then that's not the rule. So you proved it false. So Prolog would come back and say, no, not all students have to take joint seminar, because there's cases in which students have not taken joint seminar and they've graduated. So the second part of the resolution process, that's the first part, is figuring out if you're going to go back from the bottom to the top or from the top to the bottom. If you're going from the bottom, you're going backwards. If you're going from the top, you're going forward to come up to a conclusion. Not given the goal, but given, asking if a conclusion is possible versus here's the conclusion, is it true or false? Prolog does, here's the conclusion, is it true or false? That's what Prolog is good for, which is primitive, actually. Okay, so the second part of the resolution process, if the goal has more than one sub-goal, then the problem exists in how to process each one of the sub-goals to get to the goal. An example of everyone has to take joint seminar to graduate. You have to go, well, what majors are they? Are they all business majors? Or are they computer science majors? And then we start looking at the sub-goals. You can break it out and say, well, if we substitute in a business major, then they don't have to take joint seminar. Then, okay, but if this is a CS major, then they do have to take joint seminar, which means then you're basically changing the rule system as you're substituting in the rules, and then you're making arbitrary decisions that, again, are going to affect your results. So you're not going to basically rely on Prolog to answer precisely every single question without actually analyzing the process that it's going through. So the depth-first search versus the breadth-first search, which are kind of two separate concepts of AI in terms of searching that you're going to get in the searching chapter when you read it. So depth first. It first finds a sequence or a match for the first sub-goal and then continues down to all of the subsequent sub-goals. Or breadth first, process all the sub-goals in parallel. So do them all together. Which one's going to give you better results depends on how you've designed the system. Prolog designers went with a top-down, backward chaining. So it changed from the facts up to the rules. Depth-first resolution process. So it's going to start with a sequence of sub-goals and do substitutions. So if I went back to the Mary and the Susan or whatever it was, the people that play the flute, the woman who plays the flute, if there's no correlation, first thing it's going to do is going to find a fact. Is Mary woman or Mary play flute? That finds, oh yeah, Mary plays flute. And then there's an easy answer right there. It's going to come back and says, yeah, Mary plays the flute, which is the easiest way of resolving the problem. If it can't find that, then it substitutes the rules. As it goes through the rule system, it's going to find out that Mary likes pizza, and everyone who likes pizza plays the flute. Therefore, Mary must play the flute in terms of the connection. So it depends upon how everything is written, however, whether it's going to find it or not. So you can change the process, however, not highly customizable, but you can actually make some adjustments with it. So in the backward chaining example, Uncle X Thomas, male X with sibling XY, has parents Thomas Y. So to find X to make Uncle X Thomas true, it would have to go first find an X to make male true. So it first finds the first fact that's in there that makes it male and make it true. Then it's going to find the Y with the sibling XY to make it true. So it purely substitutes the fact in to another rule to see what else it needs to put in. Then checks that the has parents Thomas Y is true. If it doesn't, it recursively searches through until the rules and effects are all reached, everything is resolved, and then it comes back with an answer, which is what's referred to as backward chaining. So here's an example, and this is the default behavior for how Prolog works. So consider the database. We have a mother Betty Janet, then we have a mother Betty Steve, then we have a mother of Janet Adam, and then father Steve Dylan. Anyway, long story short, we have the association with the mother and the father that make up the parents, and then we have the grandparents that have two sets of parents on both sides. And the goal is grandparent X Adam. So we wanted to find out who's Adam's grandparent. Excuse me, the grandparent for the combination of X Adam. So then we first go through the rule system. So Prolog proceeds by attempting to match the goal clause with the facts. So it looks at the facts first in this concept. And it's going to fail it because it's not in there. There's no Adam in there. Well, there's an Adam, but there's an X for it. So failing this, it attempts to find the rule with the left-hand side consequence that it can use to substitute in and unify the goal clause. So it's going to try and derive the fact from the rules because we don't know this yet. So then it matches the goal with the grandparent XZ. We found an X. So where Z is instantiated by the value of Adam in the given goal. So we put Adam in there. Now we have grandparent X Adam that's going to be substituted in. So to prove the goal, Prolog must also satisfy the sub-goals. So then it'll check to see if the sub-goals also are satisfied. So parent XY and parent XY Adam, if that's in there. And it's purely checking to see if the fact is true, if it exists in the database. If it doesn't exist in the database, we can't tell if it's true or false, actually. So then we substitute in using a breadth first, which means we're going to go through everything step by step. And attempt to satisfy the first sub-goal that it encounters, and then the first parent rule that it encounters. So here we have these rules here that's going to come through, and it's going to say, well, parent, we know we're looking for the parent Y, so we're going to look for the parent XY. Then we have the mother XY that's going to go with it. So we satisfy the sub-goal. And then now the database first encounters the fact that the mother, and it finds mother Betty, Janet in there. And then it's going to check the sub-goal of that, substitute X for Janet, Y for X for Betty, Y for Janet, and proceed forward to the next step. This gets a little bit tedious after a while, so I'm going to kind of skip through it. You can download it, go through it at a slower pace, actually put it into Prolog if you want to, see how it works. You have to do this for your own family, or make up a family if you don't have a family. So you're not graded on how many people are in your family, however. Alright, so you can just make up an artificial family if you want to. It's artificial intelligence class, you can have an artificial family. So, as we go through all the sub-goals, we're doing the same thing, but step by step on each one of the levels for substitution and solving the problem. We can look at it sort of like this, if we outline it. And here I'm going to kind of step through it and reach the conclusion at the end. And we can come back through, and Prolog is going to come out with a yes, probably. Oops, there we go, wait a minute. The last step, mother is Janet. Mother of Adam is actually Janet. So the parent exists. We can find it. It's going to come back true. If we ask for it, we can actually get the fact that who is this person that we're looking for in terms of the database. So we can solve the grandparent XY with Adam. So we can figure out who it is. It's Betty. I don't know. So we can also do lists. So this is the database part of Prolog. If you remember, I recalled in the beginning. Prolog is also used for list processing. Very similar. It's also has a subdialect of Lisp, so you can write Lisp horn clauses and Lisp list phrases in Prolog. So it consists of 0 or more elements. So a list is 0 or more, separated by commas and closed in brackets. So the syntax is slightly different. We don't have the opening, the brackets, we have solid brackets. So the empty list is empty. So we have the head and the tail. So the head part matches the first element, or the head, and the T matches the tail part. So this should look a little familiar. I just went through this yesterday with Scheme, actually with Lisp. This is the Lisp part, which makes the language very similar. So, which is why the languages themselves are pretty easy to learn once you figure out one of them. If you've used Lisp, you've got them all figured out in terms of list processing. Prolog added the database and the knowledge database and the question answering and the rule base. So a Prolog list, to further illustrate Prolog's list notation, consider the following goal. We have a list that equals 1, 2, 3, 4. The head is 1, the tail is 2, 3, 4. If we put this in, Prolog is going to come back and say, yes, you gave me a list, okay. And then here we can say H1 is equal to 1, H2 is equal to 2. So we can change it, and we can go tail is 3, 4, and come back and say yes. So we're just building the list in two separate pieces. So here's where Prolog comes in handy, and this is the same stuff. Slightly different syntax, but the same stuff that Lisp does. We can append. And the difference here is we have more functions. In Prolog, we have a lot more functions than we have in standard common Lisp and also Scheme. So some people use Prolog for list processing as well. So a lot of people say, well, Scheme doesn't do the knowledge database, but Prolog does, and Prolog does lists, so why don't we just use Prolog? So there's a little bit of overlap. It's kind of like the differences between, Java and C++. We can write the same program in both languages, but one of them is going to do something a little bit differently than the other one does. In terms of artificial intelligence, that's what I'm trying to explain. It's like you can probably write the same program from Scheme in Prolog. It's going to work, and also Lisp. But it's going to be slightly different syntax and maybe different purpose. So here x is going to be equal to 1, 2, 3, AB. So again, we just have objects or items. We don't necessarily have data types. So a list can have anything in it. We can append we can append here, so we can put AB and x. We're appending 2x with 1, 2, 3, AB. So we can take these two and put it together. And so we can append here, we say x is equal to AB. Then it'll come back and say yes. And basically, every time you put something in, it's going to come back and go, okay, unless there's an error to it. If it can't append it, it's going to say no. So it's going to come back and say yes or no to us. So here we can append with a list. So we've got two lists being appended together, being assigned to another list. We have a semicolon here that instructs Prolog to find another solution. So if we said append, if you type this in and you press return, it's going to come back and say, okay, I've defined x, or x is this, y is this, x is this. It keeps building it step by step. This is the part that's different from Scheme. When you put it into Scheme, it just takes it. When you put it into Prolog, it evaluates every single step, because you can go backward or forward through the steps of the evaluation. So it's a slightly different format. So a lot of people just do put the semicolon in and say evaluate all of it right now and treat it like Scheme, essentially. Otherwise, it's going to step through. I added the first item, I added the second item, I added the third item, because it's logic-based. Because I don't want one moment of time you might want to stop halfway through the list edition and ask it a question. Is it in there yet? Is it in there yet? And it comes back and says, yeah. So you can actually do more analysis on the list in terms of the logic of the order of the list, contents of the list, does it match something else in the database kind of thing as it's going through. So a little bit different. So you can define a map append. Map append.pl is going to append one list to another list. Excuse me, map my append is what I meant to say. Same thing we did in Scheme, but instead of calling it with an SCM extension, we have a PL extension that shows up on the end of it. So here's the execution of the map append. So in our version, there's a file open. It's a GUI-based program, and if you look at Strawberry Prolog. In some of the other Prolog versions, it's just a command window. and you'd actually use the word consult. And this is really a function call. It says consult, which means bring in, open up, and load up in here this PL file. And it comes back and it'll say, yeah, I got it. And then you say, well, okay, my append, and you're running a function. You're running a list function. So as I said, but you can write functions in Prolog as well. You can run it inside of Prolog, and after you've already loaded it, because you've consulted it, or you've opened it up and you brought it in, depending upon the syntax of the interface you're working with. And then you can run it and append some stuff to some other stuff, and it'll come back and say, yeah, as long as it's correct. So you can define here, here's another function called myReverse that takes a list and just reverses it, puts it in the opposite order. This is the function. So it sort of looks like, consult, my, append. So in here we can do we can actually nest functions inside of function calls if we want to. We can write them all separately. Execution of myReverse, and I don't have the function written out, but you can write. You'll have to write a couple of functions in Prolog actually, which you can consult several different sources for, by the way. But here we have myReverse with this 2 items, so it's going to run it. It's going to come back and say yes. So x is going to be equal to 3, 2, 1 instead of 1, 2, 3. So you can sort of see the simplistic feedback it gives you. That's meant to be, true or false, essentially. Comes back, and if it passes, it's true. So let's apply it towards problem solving. So we have this 8 puzzle, same puzzle we saw before in a previous example for another language, in which we've got the pieces here. So the 8 puzzles is a classic search problem, so it's easily solved in Prolog. So the puzzle is a 3x3 grid with 8 tiles, number 1 through 8. The possible configuration is shown on the right. So we have a starting position, and we want to go from a starting to an ending position, same as before. So the 8-piece puzzle consists of finding a sequence of moves that transforms the starting configuration to the ending configuration. We have the start and the goal. Same example as we've seen before. Here's one solution to the problem. We start here, we move to the left. I'm going to actually kind of scroll through this till I get to the bottom. Move to the right. This is a exhaustive search technique where we're doing a plain old search for it. And then we have a partial depth first tree that comes out of this. We can put all this stuff into Prolog, and then we can have Prolog do it for us. Give us the sequence that we need. And here's how we do it. So we solve it. We enter a starting puzzle. Here's the entering, and it's 2 lists. Actually, it's 3 lists. 3 lists of 3 characters each. So we have 1, 2, 3, 4, 5, and 6, 7, 8. And then we enter the goal puzzle. And here's the goal puzzle. And the Prolog will search through the database to find all of the other combinations that make it so we can go from the start to the goal. And it's going to find it in the order in which we've put it in, which is going to be the depth first. So it's going to actually find it in this particular order, partial depth first search. So in doing that, we have the solution. So solving the problem, Prolog is going to come back and say, here it is. It's 1, 2, 3, 4, 5. This is the solution. So we represent the puzzle using a list of 9 numbers with 0 representing the empty tile. And then here are the move sequences. So we can move the puzzle using rules of the form move puzzle 1, comma puzzle 2, where there's 24 of these all in all, where this puzzle will go to this puzzle, which will go to this puzzle, which will go to this puzzle. So as long as you know all the different combinations of the moves, you put all the different combinations of the moves into a Prolog database. You have a starting position and you have an ending position, and you just tell Prolog to go through the rule set, apply all the changes, so it knows which sequence to get, and what you're learning is the sequence. So it's going to print out the sequence for you so you know how to move the puzzle to get from point A to point B. So it's kind of a simple example in terms of using it to figure out the logic. And then you have to wonder, well, is this really thinking for a human? It is, actually. Except for humans would make the wrong mistakes because they don't necessarily know the right set, how many ways to move it appropriately so that can minimize the number of mistakes you're going to make. So make it correct. So for example, the following 2 rules describe all the moves that can be made with an empty tile in the upper left-hand corner. This is just an example. So you know the sequence of steps. So the solve rule is the workhorse of the program, and it's going to be the rule that's going to be solving the puzzle for you. So to solve, you have the depth, the bound, all the information is putting here, starting position, the goal position, a list of the states for the inputs, a list of the outputs, what are you going to get after you moved from one state to another state. The depth is the current depth of the search, and the bound is the depth bound, how many resolutions you're going to get for the search space. So we have the solve, and we have the solve kind of pseudo code that gives us kind of the way that Prolog would actually attack the problem. So it's just an example of showing you how you could apply the concept to a problem solution. So there's a Prolog program for practically every puzzle out there, actually. So it might be interesting to find some of the puzzles and run through it, and you'll see this makes solving the game a lot easier. So there's a chess game one, there's checkers, there's these puzzles, so Prolog's good for solving problems that the human can't necessarily do correctly, because you're not necessarily going to think of all the different sequences. You're just going to make a move based on the current data, but one move is going to lead to another move that's going to lead to another move. So in a lot of ways, the logic of it is mimicking human thinking, which is how it ends up in the artificial intelligence category. Prolog also does arithmetic. Not to say that arithmetic requires logic, but it has the capability of doing arithmetic. Arithmetic expressions are evaluated with built-in predicate is, which is used as an infix operator. So we say the variable is expression. So here we have an example, x is 3 times 4. So now x is 12. So kind of different. Is the infix instead of using a plus or a sum. And we say is actually very scheme-like if you think about it, because it's hybrid between scheme and Lisp. So is the function. It's going to say evaluate this expression and give me the answer and assign it to x. So it comes back and says yes. Prolog has standard arithmetic operators for plus, minus, division, everything else. We also have different applications that this falls into. So in terms of Prolog applications, a lot of our intelligent systems, complicated knowledge bases, it can actually be used for neural language processing as well, and logic analysis. If you imagine Siri could be a Prolog database, because Siri is just a bunch of data. Where does she get the data from? The internet. She's a search engine. So she goes out and she finds stuff, and then she has rules. If you ask a question, then depending upon the question, it applies a rule to the question. She finds the rule that matches. She searches for the data that applies towards the rule, and she delivers it to you. Here, I have found 4 restaurants that serve this. And then it basically is a Prolog. It could be programmed in Prolog. I'm not saying that it is. But you could write your own Siri program that is doing natural language processing in Prolog, actually. Because what you're doing is you're taking a statement and you're coming back with an answer, and you're performing logic on it, logic through a search engine. So that might be an interesting application, but I'm not going to have you guys write that. It would be way too complicated. But you could definitely program it in a Prolog environment. So some conclusions about Prolog. Strengths of the language. Strong ties to formal logic. It does do the connections and the synopsis, and it mimics human thinking. Many algorithms become trivially simple to implement. It takes the fun out of all the games that you might want to play, because you just put it into Prolog and it'll tell you exactly what move you should make given the positions that you're in terms of a chess game or another type of game. Weakness. Complicated syntax. Some people find it complicated. It doesn't follow any standard, doesn't follow Lisp, it doesn't follow Scheme. It's Prolog. Again, another language. And difficult to understand programs at first sight. You don't even know what the program's doing. It's not labeled something like, well, it could be labeled something, but it might be difficult to understand what the program's actually doing. Some issues might come up in terms of what applications can Prolog excel at. Logic. That will it do a Siri thing, but will it do, or Ask Jeeves, a Prolog kind of thing. Will it be good for function programming? Does it handle recursion unless minimally? You're going to want to use Scheme if you're going to do a lot of recursive functions. Is Prolog suited for large applications? Probably not. It's working in a proprietary interpreted environment that doesn't have any memory management, doesn't do any type of variable. It doesn't support imperative languages either. And would binding the Prolog engine to another language be a good idea? Definitely. So it's a hybrided kind of language where it might make sense to write some parts of it in Prolog and then some parts of it in another language, so you can combine the best of both worlds. Prolog is only good for logic programming, by the way, not good at most other things. So it can be used for minimal functions, but it doesn't support all the memory management features that Scheme does for large chunks of data. So. Alright, so we have an assignment that's based on Prolog, and minimize this window here. I'll let you guys experiment with it. So what we have for today, actually let me pause this video here before I